Okay guys, one last note before we do 4.3. On 4.2, you may be asked to describe a transformation and state the domain and range. The rules are really similar to your rules for every other kind of function. Numbers in front are vertical stretches. Negatives could be reflections. Numbers added at the very end will be vertical shifts. Numbers added in the exponent in this case will be horizontal shifts. So we'll just do one of these before we roll in. -4 times 2 to the x minus 3 plus 1. The negative, so our parent function is whatever number is raised to the x power. So the negative is a vertical reflection. The 4 is a vertical stretch by a factor of 4. The minus 3 in the exponent is a horizontal shift. It's right 3. And the plus 1 is a vertical shift of up 1. So this is really similar to the way we did it before. It's just going to be applied to these exponential functions. Now, what were the first two sections of this chapter? Inverses and exponentials. Now, if we combine the two, we would have the inverse of exponentials. Now enter logarithmic functions. So the logarithm is the inverse of an exponential, but it's also an alternate form of an exponential for conversion purposes. So we can talk about that a little bit. For all real numbers y and positive numbers a and x, where a is not equal to 1, y equals log base a of x is an equivalent form of x equals a to the y. So the base of your logarithm was the base of your exponential. The goal of logarithm form is to get the exponent by itself. And then the thing that was isolated before goes inside your logarithm. So first we're just going to practice rewriting. So 2 cubed equals 8, rewritten in logarithmic form. Log base 2, so the base is the same. Your 8 is now inside the logarithm and your exponent is by itself. X to the 1/2 equals 9. Log base x of 9 equals 1/2. 5 to the x equals 1/25. I'll leave 1 for you to practice. Now, if you can go from exponential form to log form, you should be able to go from log form to exponential form. Log base 3 of 81 equals 4 is the equivalent statement of 3 to the 4th power equals 81. So your base is the same, your number that was isolated is your exponent, and the number inside is now by itself. Log base x of 32 equals 5, x to the 5th equals 32. And again, I'll leave 1 for you. These should be the easiest points on the test that you come across. Now, solving logarithmic equations for now is very easy. All you're going to do is convert them to exponential equations and solve them the way you would have solved the exponential equations in the last section. So log base 8 of x equals 3. You rewrite as 8 cubed equals x, and you solve for x accordingly. Here we'll just take 8 cubed, which is 512, and we'll be done. Now, more realistically, you may have a little more work to do than that. Log base x of 8/27 equals -3. We can rewrite to x to the -3rd is 8/27. This is really x to the -1st cubed equals 8/27. So 1 over x cubed equals, I need common exponent, so this would be 2/3 cubed, because again, 2 cubed is 8, 3 cubed is 27, so that's how it works with fractions. You would take the cube root of both. If my exponents are equal and my equation is equal, I'd have 1 over x equals 2/3. And of course, if I want to flip the left side to x over 1, I would also have to flip the right side, so x is 3/2. But otherwise, these are, except for converting, these are more equations that are similar to the ones you've done in 4.2. Shouldn't be hard. We'll learn some actual techniques for solving these. The rewriting isn't what we really need to do, but it will work for now. In 4.5, we will address what's actually happening when we rewrite and how this works. So because a logarithm function is the inverse of an exponential function, that means we can find the graph of a logarithm and the domain and range of a logarithm by taking an exponential and using the idea of inverses, switch the domain and range, take x and y values, and switch them. So if you recall, 2 to the x looks something like this. Kind of parabola-like on the right side, but it flattened out on the left. Because it had some x and y values. 2 to the 0th was 1, 2 to the first was 2, squared was 4, 2 cubed is 8. But to the negative 1, first power, it's 1/2, negative second, 1/4, etc. So that means log base 2 of x, so when the bases are the same, this is the inverse version, takes our x and y values and flips them. So instead of 0, 1, it's 1, 0, 2, 1, 4, 2, 8, 3, so we can graph those. And 1/2, negative 1, 1/4, negative 2. So what's actually happening is it's leveling off at the bottom instead of the left. Instead of curving out and up on the right side, it's now curving to the right as it goes up. And remember that from chapter or section 1, there's this line of symmetry, and you can even just look at these across this line of symmetry and see they are indeed inverses because of that law of reflection across the line y equals x. Now, we can talk about what logarithms look like, but just like exponentials, there's not a whole lot of options here. We just saw what log base 2 of x looked like on the other side. Log base 1/2 of x will do the same thing, kind of, but it's the inverse of 1/2 to the x, which gets big on the left side and small on the right side. So this thing ends up looking like this. It's a reflection. Now we'll see, so besides these two, so we just saw this other one, is this. That. So this is the only two ways it can look. Negative log base 2 of x. We'll talk about our properties for a second. If we took this log base 2 of x and flipped it, it actually looks like this one. Negative log base 1/2 of x looks like this one. There's a reason for that. We'll see it in our rules when we get there. But before we get to the rules for logarithms, let's talk the domain and range. Because the domain of x, just looking at the domain here, it's from 0 to infinity, but the range is negative infinity to infinity, which is backwards from our exponential function. Similar to the way we had transformations for the exponentials at the very beginning of this video, we have transformations for the logarithms. So again, your parent function here is log base of the number of x based on what you see. So starting from log base 2 of x, what's actually happening here? The -3 is moving it right 3, gives us log base 2 of x minus 3, and then the +4 moves it up 4. It's kind of an informal notation, but it works. And of course, negatives and numbers multiplied in front create reflections or vertical stretches and shifts. And we'll get to the logarithmic properties that mirror our exponential properties in the next video.